My name is Susan Phillips, and I'm a reporter with a public radio station in Philadelphia called WHYY. And right now I work on a joint project between WHYY and NPR News called State Impact Pennsylvania, which I've been, for the past year, we've been covering energy in Pennsylvania, which, of course, everyone knows has to do with Marcellus Shale and hydraulic fracturing. So welcome to this panel today with the AGU, which we have three very highly qualified folks in the world of science and hydrofracking and natural gas development. I'm going to give the mic to Howard Gruenspecht. Just a quick note about Howard is over the past 30 years, he's worked extensively on electricity policy issues, including restructuring and reliability, regulations affecting motor fuels and vehicles, energy-related environmental issues, and economy-wide energy modeling. And I guess he's going to really solve that question for us about how much Marcellus Shale is, how much gas is in the Marcellus Shale, and what can we hope for?
You'll be disappointed, and different people hope for different things, as you might imagine. But I thank you for the kind introduction, and I thank the AGU for inviting me today. Before turning to substance, I should note that EIA is a statistical and analytical agency within the U.S. Department of Energy. Our mission is to collect, analyze, and disseminate independent and impartial energy information to promote sound policymaking, efficient markets, and public understanding of energy and its interrelationship with the economy and the environment. By law, our data analyses and forecasts are independent of approval by any other officer or employee of the U.S. government, so they shouldn't be construed as representing the views of the Department of Energy or the administration. That's why I don't have a scheduling conflict today. As requested, my remarks today focus on the role of natural gas, shale gas in particular, in the overall U.S. energy picture. I'll start with current data, which reflects many fast-moving developments. Then I'll briefly discuss natural gas resource estimates and EIA's longer-term projections for natural gas production and use in the United States. All right, this is really, I think current data really provides a reality check and an important anchor point for an understanding of how natural gas fits into the overall U.S. energy picture. I'm not giving a test on this, don't worry. It's a good starting point for looking at natural gas and many other issues. It's sort of like the single energy chart that I guess if you wanted a snapshot of U.S. energy. So the primary energy sources are run down the left-hand side with quantities shown in quadrillion BTUs or quads. We haven't caught up with the international system yet. In rough terms, a quadrillion BTU is 172 million barrels of oil, 50 million tons of coal, or a trillion cubic feet of natural gas. So a quadrillion BTU is a lot of energy. The sectors that use primary energy are shown on the right-hand side, again with the quantities of primary energy used, and the spaghetti is sort of the source and sector links. For example, nuclear is the easiest. 100% of nuclear energy is used in the electric power sector, so there's 100 there. And on the other end, it provides 21% of the energy input into the electric power sector, so there's a 21 there. That's like the story of this. A look at the spaghetti in general shows you that many energy sources are tied primarily to one sector. So nuclear is tied to electricity. Over 90% of coal is tied to electricity. Oil is tied heavily to the transportation sector. Natural gas is sort of unusual in that its use is pretty spread across the electric power sector, residential and commercial buildings where it's used for heat and space heat and water heat mostly, and the industrial sector. So about a third each there. Very little in transportation, where its use of natural gas is largely limited to powering the movement of natural gas via pipelines. That's a transportation activity. There is considerable interest both in the private sector and among policymakers in exploring or encouraging the greater use of natural gas as a transportation fuel, but that's not really the current situation yet. but natural gas is sort of widely used in the other sectors. So this is like your USGS Geological Survey kind of picture of natural gas. Natural gas occurs in a variety of settings. Conventional natural gas, which accounted for virtually all production up until 1990, is gas that's migrated from its source, and it's accumulated in a reservoir where it's trapped by an impermeable cap or seal. So that red natural gas under the impermeable cap or seal is like a conventional natural gas. So gas forms someplace, it migrates, and then it accumulates under a seal. And when production wells are drilled through the cap into the reservoir, kind of like the picture in the movies of like Spindle Top, where they drill the well and come shooting out the top, conventional gas flows readily to the well. Conventional gas is sometimes divided into associated and non-associated gas. There's gas that comes with the production of oil that's associated, or whether you have natural gas alone. Shale gas was first developed in the late 1990s and has been primarily responsible for the boom in domestic gas production over the last 5 years. It's really at the opposite end of the resource spectrum from conventional natural gas. Shale rock, which is the gas-rich shale in this little schematic picture, is a continuous type resource that is itself the source of the gas that is trapped within it. So while conventional gas sort of migrates from where it was formed to where you get it from under a cap, shale is where the gas was formed, and shale is where the gas stays because it hasn't moved much. Gas does not flow easily within shale rock, so hydraulic fracturing is required to create passageways for the gas to flow to a wellbore, and you really can't produce that gas without fracturing the shale to make the gas flow. Horizontal drilling is also used because obviously that gives you more surface. There's also other types of gas, tight gas, coal bed methane, but they're not important to today's talk, so I won't tell you about them. There's a lot of shale gas, a lot of shale plays in the United States. Things actually began in Texas in the Barnett Shale, but there's shale all over. There was tremendous success in the Barnett and certainly encouraged companies to look in other shale formations. And again, they're everywhere. And the Marcellus in the Appalachian region is particularly very popular these days, and I guess is the main subject of this session. And the Eagle Ford in Texas is very popular. There's also a lot of drilling in shales for oil in various places and liquids. It's not just natural gas. So what's happened with shale gas? This is a pretty up-to-date picture of the growth in production, and it's really pretty astounding. I mean, from at the beginning of 2007, production under 5 billion cubic feet a day, you now have production over 25 billion cubic feet a day. And you can see that the Barnett, sort of the layer above the immediate bottom layer, sort of where things began, but that you have rapid growth in the Marcellus, in the Haynesville, and in the Eagle Ford are very important growth areas for shale. So it's really growing very fast. Between 2006 and 2010, shale production grew greater than 50% each year. So this is a look at sort of natural gas and crude oil prices on an energy equivalent basis. The top line is crude oil, Brent crude oil in particular. So that's about $20 a million BTU, which is about $120 a barrel, which is about what it is today. It's 119. And then underneath it, you have gas in various places. The red line is natural gas in Japan. That's mostly liquefied natural gas sold under contracts that are indexed pretty closely to oil, so not surprisingly, those prices pretty close to oil. The middle group of them are some European spot prices. Actually, in Europe, people are paying a combination of spot prices and contract prices that are somewhat linked to oil, but not as strong as in Japan. And then the bottom two are the U.S. Henry Hub and the Canada Hub in Alberta. And you can see that prices are like $2 a million BTU now, which is the equivalent of $12 a barrel of oil in energy equivalent terms. So there are differences in prices across regions. The decline in the U.S. prices reflects that dramatic increase in shale production. Currently, the wholesale price of natural gas in the U.S. is about 1/8 of the price in Japan, and about a quarter, less than half of the price in Europe. It's actually like a quarter right now. Differences in natural gas prices across the world regions arise from the relatively high costs of moving natural gas over extended different distances, which may involve the significant costs of liquefaction. And there is talk in the U.S. about possibly liquefying and exporting some gas, and these price differentials are part of the reasons. I guess the question is, what will the price situation look like in the future when such an opportunity might become available? So delivered gas prices in the United States have been declining since 2008, and that certainly has provided important savings to U.S. natural gas users. In 2011, our consumption was about 22.3 trillion cubic feet of natural gas, and the average delivered prices in 2011 were about $4 per thousand cubic feet lower than they were in 2008. If you do the math, that suggests that people who bought natural gas spent about $90 billion less in 2011 than they would have spent for the same amount of natural gas had they paid the 2008 prices. So households saved about $15 billion on their heating bills. Costs for commercial buildings, which includes offices, stores, schools, hospitals, other non-residential stuff, about $11 billion. Industrial users saved about $31 billion. The electric generation sector saved about $33 billion on their gas purchases, but this is likely to understate actual reductions in electricity bills because in many areas of the United States with competitive wholesale electricity markets, natural gas generation is typically the marginal source that sets the wholesale price for all generation. So, and again, current prices are actually kind of well below the average in 2011. I think you can see that from this graph. So presumably this year, consumers are reaping additional savings. So there is, an economic aspect of this. I'd now like to shift from data to projections and focus on the early release reference case from our annual energy outlook. That's put together assuming no changes in current laws and policies, continued trend improvement in technology, but no real technology breakthroughs. The full outlook is going to be released in probably later in May, maybe early June if things slip. And it includes many alternative cases in recognition of the uncertainty inherent in making projections about energy markets. You certainly have to keep uncertainty in mind when you're looking at these projections or any other projections of energy markets. A very wise person once noted that prediction is very difficult, especially if it's about the future. It sounds like something Yogi Berra might have said. I grew up about 3 miles from Yankee Stadium when Yogi was playing. Shows you how old I am. But the observation was actually made by the eminent physicist Niels Bohr, and he's certainly right. So again, no facts about the future, as the first administrator of my agency said. So this again shows the growth in estimated natural gas resources over additions of our energy outlook going back to 2000. And one of the horrible things about working in an agency like mine is that we are brutally honest about the past projections that we've made, and we publish elaborate retrospective looks at them, and but you can see that going back to 2000, there's been an increase in the estimated technically recoverable resource. There's sometimes a lot of confusion about reserves and technically recoverable resources. It's very political. I'm not getting into that, but technically recoverable resources is sort of the broad measure of sort of how much is there and recoverable without regard to economics. And needless to say, while all energy projections are uncertain, this is really uncertain. And one thing you'll notice is that the red stuff, if you look at this, the blue at the bottom are the proved reserves, all types and locations. And that number's in our current outlook, our 2012 outlook, we're using a number of about 273 trillion cubic feet, which is a little bit more than, well, it's 10 or 12 years of current production rate, which is in the low 20 trillion cubic feet a year. Now, that number has risen steadily since 2000, even though we've produced over 200 trillion cubic feet of gas since 2000. So sometimes there's a real confusion in the public's mind about reserves. People have this sort of ice cream tub view of reserves, that the reserves are how much ice cream is in the tub. And if you have 200 to start with and you scoop out 200, there should be 0 left in the tub. But in fact, this is a magic tub. Or it's not a magic tub, it's an economic tub. People, do exploration, development, develop new technologies, and the tub actually has more in it now than it had when we began. But there's also a lot of unproved other types of gas. And then finally on top is the shale gas, which is pretty attractive and a lot of attention. The estimate of unproved shale resources we're using in the latest outlook are lower than those used in last year's outlook as a result of some new information from the U.S. Geological Survey and some other additional information that's become available. And the biggest single change, the reason I'm bringing this up here, is a reduction in the Marcellus resource estimate. Our latest projections are using about 141 trillion cubic feet. It's well below what we used last year, but it's well above the mean estimate of 84 trillion cubic feet that USGS published in the summer of 2011. So while we're well above the USGS estimate, we're well below some of the other estimates that have been published by people in Pennsylvania and elsewhere, really, about this. Believe me, since putting this out, I know that changes or differences among resource estimates receive a great deal of attention, but resource estimates are not the only driver or even the most important driver of natural gas production and price projections for the next 25 years. And in fact, as I'll shortly discuss, the new reference case price projection is lower than that in last year's outlook, and the production projection is higher than that in last year's outlook, despite this change in the underlying resource base. So other things that matter are the trend in shale gas well productivity, trends in drilling costs. So again, there's sometimes a mistake in mapping directly from these resource estimates, which are highly uncertain, to price and production projections. So this is, again, our view of domestic natural gas production and consumption and net imports. Again, everything, we're mostly a data agency, but we also do this forward-looking work. So everything to the left of the dotted vertical line, that's like data, and that's like the way it is, whether you like it or not. Everything to the right of the dotted line, it's our reference case projection. I've already described that it's necessarily highly uncertain. But you can see that we expect both consumption and domestic supply to grow. We expect domestic supply to grow faster than production. We see net imports, which have already been declining, continuing to decline. And in fact, the U.S. becomes an exporter of natural gas in this particular scenario. Most of the production surplus is exported primarily to Mexico in this projection, but there's some that goes overseas in the form of LNG. This is the sort of the composition of the natural gas supply, and you can see that this thing only runs, again, 2010 is the historical line here. So shale gas was 23% of our natural gas production in 2010. You notice that it grew rather dramatically in a very short period of time. It's over 30% of our production today. Again, we expect shale gas to continue to play a very big role. Tight gas, coal bed methane, still play a big role. And overall, we expect growing natural gas production, as I've already indicated. This one here is what happens to consumption of natural gas. It's largely self-explanatory. Most of the demand growth is in the electric power sector. There's also growth in industrial demand, especially in the first decade of the projection period. I think we're getting to the end of this. This is our outlook for prices. These are annual average prices. This was put together before the recent extremely warm winter and collapse of natural gas prices to the $2 range. But you can see that gas prices have fallen a lot. And these are in real dollars, again, so these are all year 2010 dollars. But you can see that gas prices have fallen a lot since in a short period of time. I already discussed some of the implications of that economically. We in EIA think that gas prices will rise in real terms. But again, a price of $5 or $6, per million BTU, that's equivalent to $30 to $35 a barrel of oil equivalent. So, while we expect natural gas prices to rise from their current low levels, natural gas, is somewhat attractively priced. And I guess, again, it depends on some of the factors like the productivity of the wells, the cost of drilling. Certainly the resources are one factor that matter. And with that sort of context on the current and projected role of shale gas resources in production, you notice I've said nothing about fracking. I look forward to hearing, but I didn't say I would either. I look forward to hearing the other speakers, and I look forward to the ensuing dialogue. So, again, I think EIA is a great resource. You're paying for it in your taxes, so you might as well visit our website and look at some of our stuff. Thank you.
So our next speaker is Robert Jackson, and he is the professor and Nicholas Chair of Global Environmental Change at Duke University, and he's currently the director of Duke University's Center on Global Change and Stable Isotope Mass Spectrometry Laboratory.
Okay, thank you everyone for being here, and thanks also to the AGU for putting this on and the whole policy science conference in general. I'd like to talk about hydraulic fracturing itself and a little bit about some of the environmental interactions. Along with my colleague Avner Vengosh, I've been working for a couple of years on this issue, looking at what some of the environmental issues might be, both real and perceived. So we don't attend anti-fracking rallies. We don't call for bans. We're interested in if problems arise, why do they arise, and what you can do about it. I mean, ultimately, I want the science that my group does to be useful. I think that's the spirit of this conference today. Howard gave you a nice summary of the resource in general. They did ask me to spend just a minute or two going into a bit more detail on what hydraulic fracturing is. And forgive me, I know there may be a handful of you in the room who don't know this. For the rest of you, indulge me if you would. So hydraulic fracturing is really just part of the process of getting unconventional, especially unconventional resources out of the ground. It's really one step. The first step that's important after identifying the resource is horizontal drilling that Howard mentioned. This is a technique that goes back to the 1980s or so. The ability to drill down, if you will, a mile and then out sideways a mile or two, following a layer of shale, for instance, if we're talking about shale gas, that might only be 100 feet thick when you're down 6,000, 7,000, 8,000 feet underground in a layer that's moving like this. So it really takes remarkable three-dimensional seismic technology to do this, and technology is one of the main stories in this issue. I mean, it's an incredible increase in technology that's made this resource available to people. So I like to use an analogy sometimes that this is like a birthday cake. Now, I don't know about you, I like cake, and I especially like the icing. So imagine that you've licked all the icing off the outside of the cake, and all that's left is that thin layer down there in the middle. So if you drill a hole down into that cake, you only intersect that layer in a very small area. But if you can drill down and then follow that icing sideways, that's really what this is about. So that's the horizontal drilling step. Then after that occurs, you have to free the gas. And this is where the step of hydraulic fracturing comes in. So typically, several millions of gallons of water, sand, and chemicals, we'll talk about this a bit, are pumped underground at very high pressures that you might see at the deepest point of the oceans, for instance. And they're pumped underground and staged and are used to crack open that rock. And it's that step, that cracking open of the rock, that allows the gas to flow back to the wellbore and up to the surface and be commercially available. So it's really those two things. Hydraulic fracturing is just one part of the process, even though it's become sort of a catch-all term for this process in general. All right, so environmentally, you can already see a couple of ways that this might affect the environment. First of all, the water that's found naturally deep underground is is, in general, pretty nasty. It tends to be very salty. In some cases, it can have naturally occurring radioactive materials. It's not a resource that we use for drinking water, and it's not something you want mixing with drinking water or with your surface waters in streams or rivers. Some of that water comes back to the surface during the production process. Then there's also the water itself, the 2, 3, 4, 5 million gallons of water and the chemicals that are put into it that are used to hydraulically fracture the well. We'll talk about those chemicals. Most of them harmless, some of them not, and how you also don't want those mixing. There's the water requirement, and then there are also air emissions I'll mention briefly. So up at the surface here, you have everything from perhaps 1,000 trucks coming in with different parts of the stage. You have other diesel sources, compressors. You have volatile organic carbons that might be coming off during the completion stage. So all of those things, we're really trying to get a handle on the science, how much of those are lost to the atmosphere, and what's the fate, and ultimately what companies can do, what progress is already being made about capturing those materials. So that's just a little bit of background, I guess. All right, what are some of the public concerns about this process? Here's a list. They include water for hydraulic fracturing. I've already mentioned 2 to 5 million gallons a well. In my view, this is a serious issue, but it's primarily a serious issue in the drier parts of the country. So if you're talking about the Eagle Ford, South Texas, for instance, where most of this water is coming from groundwater pumping, that's a real issue. If you're talking about Pennsylvania or my home state of North Carolina, it can be an issue if companies draw too much water from a particular resource. That happened early on in the Marcellus. But the Department of Environmental Protection in Pennsylvania recognized that and stopped that. So in relatively water-rich areas, in my view, the water supply issue is not the primary concern, although it is a concern out west and again, in dry areas. All right, another one I think really is something that we're tackling now is the disposal of produced waters. So the produced waters are what come back to the surface. It includes a mixture of the hydraulic fracturing fluids themselves, a couple million gallons in some cases, and then the long-term flow back to the surface of natural formation waters, that very salty water that's been underground for millions of years in some cases, comes back to the surface with the well. And you have to do something with that water. You can't just release it into the environment. And it's not only very salty, it can contain radioactivity, it also has metals and other things that we don't want in water, barium, arsenic, bromine. We'll talk about some of these and why we care about them environmentally. We'll talk about drinking water very briefly today, air quality interactions, and something you've all probably heard a lot about in the last few months. That's seismicity, tremors, earthquakes associated really with the wastewater disposal step, not so much with hydraulic fracturing itself. So when this wastewater is pumped deep underground, very high pressures and high volumes, the rock faces can slip against each other. There have been many cases of tremors associated with that. There have not, to my knowledge, been any kind of large-scale damaging earthquake associated with that. That's something I believe a problem that can be managed through monitoring and such. So let's step through a couple of these examples and what we know about them, and what some of the uncertainties are. Okay, first of all, what's in hydraulic fracturing fluids? So you often hear that 90% plus is water, 5 to 10% might be sand and other proppants to keep those cracks open after they form, and it's only 1% that's the chemicals. And that's true, but if you put 5 million gallons down the well, that's 40 million pounds of material, and 1% of that is 400,000 pounds of chemicals. So this is a lot for each single well. This was a report that came out last year, 2,500 different products containing about 750 chemicals. Most of those chemicals are harmless. Some of the examples include salt, citric acid, walnut shells, coffee, my personal favorite. Some aren't so harmless. I mean, carcinogens, benzene as an example, naphthalene, diesel in rare cases, hazardous air pollutants. There's a fairly long list of these that are used too. Toluene and hydrochloric acid are two examples, and many other chemicals, ethylene glycol, lead. And these are put in for different reasons. They're put in as biocides to kill the microbes that might give off hydrogen sulfide gas, for instance. They're put in to change the viscosity to increase the flow of the water. They're put in as corrosion resistors and things like that. So there's a whole suite of reasons for using these chemicals. All right, what's in the produced water? So not only might you get some of that, and you do get some of those fracturing chemicals back, but you also get the natural water. In the Marcellus, for instance, the water that's found deep underground is 10 times saltier than seawater, just as a rule of thumb. It can have high bromine concentration, does in many cases have high bromine concentrations. This can be a real issue for trihalomethanes when you get to water treatment facilities and such, forming products that are a problem for human health downstream. high concentrations of some of the more toxic elements I've already talked about. A unique, not to the Marcellus, but a few places around the country is this presence of naturally occurring radioactive materials, the norms, and then also the hydrocarbon residuals, both that are naturally found and also from the process itself. All right, so you have to do something about the water, and here's one thing I want to do today is to provide some positive things that industry has done to make this better, and also to provide some of the things the examples that we don't want to do, or paths we don't want to follow down. One of the main ways that this produced water is disposed of today is through deep injection. In the case of Pennsylvania, that's essentially illegal. It's not done, at least. So for Pennsylvania, the deep injection is going to Ohio. So it's a cross-state interbasin water transfer. So that you're pumping that water back deep underground. You're taking nasty water, pumping it down into relatively nasty water. Perhaps not a perfect solution, but a much better solution than releasing that water into surface waters, for instance. All right, some states allow you to spray it on lands. So the Forest Service published a study last fall that is perfectly legal. This was a case where 75,000 gallons of this produced water was sprayed on less than an acre of land legally. Within 10 days, half the leaves dropped off, and within a year, half the trees were dead. So not something that we want to do. It is illegal in a few states, West Virginia being one of them. Okay, we also don't want this water going to municipal water treatment plants. They're not set up to handle the volume. They're not set up to handle the particular suite of chemicals that come in, and you really don't want this happening. So one of the things that sprung up in Pennsylvania, at least, in the Marcellus, is this commercial wastewater network. So these are private water treatment facilities that have risen up and are treating some of this water. I think a real scientific question here is what's the ultimate fate of that water? How much of it might then go to municipal treatment facilities or might be released to the surface. But one of the really positive developments that's come out of this is the reuse and recycling of that wastewater. So companies are making progress, taking that wastewater, using it to frack the next well. That's a really positive thing because it reduces the amount of water required and it reduces the amount of wastewater that's left over that you have to do something with. So I think some credit goes to the industry for fostering this. We've got a long way to go on that recycling, but that's the kind of example of incentives that we can provide. All right, so a few positive developments on the waterfront. Recycling and reuse of water, I've already mentioned. Greater disclosure of the chemicals in fracturing fluids. It's not true that industry gives you no information about the chemicals in them. They do have a website, fracfocus.org, that lists many of these chemicals. The states are really driving this. States like Wyoming and Texas have new disclosure laws that are requiring this disclosure, even to some extent release of proprietary chemicals and such. So I think this is great because transparency will ultimately, I believe, lead to phase-outs of the more toxic chemicals. It will put pressure on companies to find something else to use, and everybody will win in that context. There have been proposals recently, really interesting, to eliminate the chemicals entirely. So here's an Irish operation, Tambora, and their chief executive, Richard Morman, came out with a pledge last fall to say they won't use any chemicals at all in their hydraulic fracturing operations in Ireland. Now, it's a fairly unique case. It's very shallow. We'll see if they actually meet that pledge. But perhaps, again, the long-term goal is to ask not just how do we get rid of some of these chemicals, but how do we stop using them to begin with to the best extent possible. And finally, I think a big uncertainty is in the green completion step and the elimination of open wastewater pits. So there's this short period of time, a few days to a few weeks, before the well is really putting the gas into the pipeline where you get this sort of surge of a mixture of water and the chemicals and the gas. And companies do different things with that water. Some of the companies put it to an open wastewater pit where you might have volatile organic carbons moving into the atmosphere and downwind. Some of them do it strictly in closed tanks, which is a better solution, a little more expensive. All right, some of them capture the gas, some of them flare the gas, some of them vent the gas. So methane's a potent greenhouse gas, as you all know. So best practices that some companies use spread across the industry as a whole would help us make some additional progress in this area. All right, let me switch to drinking water, and I just want to give you two examples from our own research over the last year. So we have focused on people in Pennsylvania with private drinking water wells. So I live on a quiet gravel road in North Carolina. I have my own well water because there isn't municipal water available, and that means no one tests my water unless I pay for that. So we focused on the 45 or 50 million people in this country on private water wells. We did that because of the lack of safeguards compared to people on a municipal water source where there's regular testing of your water. So this is just one house, for instance, that we've sampled in Pennsylvania. So we've sampled a couple of hundred houses now, focusing on the northeastern part of Pennsylvania where the Marcellus drilling has been the most rapid, and also an interesting area because it's relatively poor, the economic benefits there are real, and it doesn't have a long history of oil and gas extraction, unlike the western half of the state. So here's a photo of Nat Warner. This is my colleague Avner Vengosh and such. So that we walk up the driveway. Every driveway you walk up has a different story, just like Susan told you. Some of them are very happy, grateful for the money, all kinds of positive benefits. Other people are bitterly unhappy, and some people who haven't signed up are also unhappy. So the whole spectrum is represented by the people that you talk to in doing this kind of work. Right, so we grab samples directly from their well. We do a few things in the field, but we take them back to the laboratory and analyze them for their salt contents, the radioactivity potentially, their dissolved gas concentrations and things like that. This gives you just an example for Pennsylvania how many wells there are. There are hundreds of thousands of wells if you go back to the beginning. And most of this action, though, has been in the western part of the state here. And again, this is the sweet spot of the Marcellus. There's some down here as well. But up here is where that sweet spot for Marcellus is and why we've been focusing on that area. All right, so what did we find? Well, first of all, we didn't find most things that we were looking for. All right, we didn't find any evidence for the chemicals in the fracturing fluids, at least for the things that we were able to look at. In this first study, we didn't look at all of the organics, for instance, the benzenes and some of the other chemicals. We didn't find any evidence of salts. The bromine, changes in salt ratios, strontium and strontium isotope ratios that give us information about water that's deep compared to water that's in the surface. What we did find, the single thing we found, is much higher dissolved gas concentrations if you were living near a natural gas well. So we asked a simple question: if you're living near a well, is your water any different than if you're living farther away? And the answer was no, except for dissolved gases. And then both for ethane and particularly for methane, you had much higher concentrations if you were within a kilometer of a well. So here's a distance to the well here in thousands of meters. There's 1 kilometer here. The y-axis, which my pointer you can't see, is methane concentrations. The gray band is interesting. That's the Department of Interior hazard mitigation band. If you're within that band, they suggest you consider taking action to vent your water or to get a different water source. If you're above that band, they recommend taking immediate action. So the only people above that band in the study were within a kilometer, and some of those concentrations are dangerous if that methane builds up in air. Right, so there's clearly something going on. The isotopic compositions of this look more like deep gas than shallow gas. So the isotopic values also lined up with not a natural, not a microbially derived source from underground. All right, so there's something going on here. This holds for ethane. All right, so what do you do with a data set like this? Well, there are lots of questions to ask. First of all, how representative is it? If this happens here, doesn't mean it happens somewhere else. So we're looking at some other plays. But one of the things, again, in the spirit of using science to help solve problems, we made a set of recommendations when this paper came out last May. One of those was presumptive liability. So Pennsylvania has something called a presumptive liability rule that says if a homeowner has a problem, like the story you heard earlier, within 6 months of a well being drilled, the well operator, the driller, is considered to be the source of the problem and to be guilty for that unless they can show otherwise. This is a great law because it fosters pre-drilling testing. So the companies pay you with your private water well to get a test, so you have a baseline. If your water quality changes, you know the source, and it's good for the companies because the companies then don't have to pay for poor water quality that they didn't cause. Right, so when our paper came up, we took that 1 kilometer distance, for instance, and said that the current distance of 1,000 feet should be 3,000 feet based on that one kilometer threshold. Governor Corbett just signed a law in September. They used 2,500 feet in between. So we made other recommendations, too, in terms of setbacks and things like that. So again, the goal here is to make the science useful. All right, then finally, my last example is in air quality, and there's a lot of work being done on that. This is a study that just came out a few months ago in an AGU publication, the Journal of Geophysical Research. It's Gabby Patron's work. This is really interesting in Colorado. So they had long-term monitoring of a tall tower, hundreds of feet tall, and they started to notice these anomalous plumes of different hydrocarbons, just depending on which direction the wind was coming from. So then they went out into the field and looked at the possible sources for that with these mobile units and found that those gases were associated with oil and gas production. So this is more sort of not a single well case, but kind of a regional, if you will, effect of extraction. So again, the case here isn't necessarily that this will apply everywhere, but it's how representative of this is this, and what does it tell us? If this study is representative, then we're underestimating the gases that are typically given off during these various steps. There's also a controversy about how leaky the pipelines are and how much methane is vented during that completion step, right when the well is first being produced. So another thing that we've been working on is to try and understand the leak rates across pipelines. This will be my last example. This is work with Nathan Phillips at Boston University and colleagues at Harvard and other places. So what we're interested here is asking, all right, how leaky are these pipelines, and what's the total amount of methane that actually reaches the atmosphere once it hits the pipeline? All right, so this is brand new technology, new instruments that allow you to take a methane measurement real time. You put this in a car with a high-resolution GPS, and you can think of this as Google Street View for methane, if you will. Drive every block in the city, 10, 15 miles an hour, and map the leaks, literally block by block. And when you get a plume, you hop out of the car, you take a bag sample, bring that back to the laboratory, my lab at Duke, and we analyze it with a mass spectrometer for its isotopic composition, which allows you to distinguish landfill gas from sewer gas from natural gas from a main. It's a delivery system. So this is a picture of the unit in the car. This is a picture of John Carr sampling in a street. We've got sensors on the top of buildings now, so this leak block by block is a bottom-up approach. You also want a top-down approach. So you can look at total buildup at night, for instance, if you want to understand the complete flux into the atmosphere. And then occasionally we get in trouble for double parking and things like that. Interesting story, though. In this case, the policeman stops, asks us, may I help you? And I explain what we're doing, and he says, I'm so glad you're here. They've been calling us about this leak for 2 years. And he said, when there's a leak, they call the fire department, they call the police department, and those leaks often don't get fixed. All right, so what did we find? Well, here's one example. Here are a few blocks in the city of Boston. You have streets with no leaks whatsoever. You have other streets where you get a leak that's 10 times the background concentration. Now, these are concentrations, not fluxes. It's not enough just to get this picture. You have to understand the flow of gas, too. But this is really useful information if you want to help solve problems and reduce the leak rate. So that's just an example. Here's the current picture for the Boston Metroplex as a whole. So we found about 2,000 to 3,000 leaks across the city. Again, the point here isn't to say we shouldn't be using natural gas. That's ridiculous. The point is to say we can take this information, use it to solve the worst leaks, to make the system better, and to make it safer. This will cut down on the number of fires, and ultimately will save some lives too. And I think if most of you can look at a map like this and say, well, if these leaks were there, why doesn't the company pay to fix them? That's the obvious question, I think. And in a case like this, my sense is that this is a matter of incentives, that the distribution companies don't pay for the lost gas. In Massachusetts, 2% of the gas that enters the state goes missing. Or it doesn't mean that 2% gets to the atmosphere, but it's unaccounted for. Well, who pays for that? The ratepayers pay for most of that. So that the distribution companies are already paid for the lost gas. So they do a good job, they fix leaks, but they focus on leaks that are associated with potential health risks, not the more chronic leaks. So again, I think it's a matter of incentives, aligning incentives to do the right thing for the environment, make it safer, and for economic reasons too. Okay, well, I'll end there. I want to finish just with a couple of points. One is that, Howard gave you this overview. This boom in unconventional energy is absolutely incredible. In 2005, we were talking about building import terminals for natural gas. Now we're talking about building export terminals. The technology is getting better. I've tried to give you a sense of some of the advancements that the companies have made, particularly focusing on water. But I also want us to acknowledge that the technology and the production has outstripped our scientific knowledge of this. We're playing catch-up in terms of some of the potential consequences and understanding where problems occur, why they occur, and where they don't occur and why. Is it geology? Is it the company that's doing it? Is it people being in a hurry? What is the cause? So there's lots of other controversies you're hearing about today, Pavilion, Wyoming, and the potential for the fracturing fluids and things like that. There's just a huge amount of science that's going on, lots of interesting questions still to be answered, but I believe a strong role for science to help provide positive solutions. Thank you.
Now we'll hear from Bernard Goldstein. And just real quick, he is the professor and dean emeritus of the Graduate School of Public Health at the University of Pittsburgh.
Thanks, Susan. I'm going to, public health is sort of answering the question that Susan's picture showed. How do you respond to someone who says, my water's dirty and it's not safe? And I think the overall bottom line is that I'm going to tell you that I don't know. We simply have not been able to do the work that one would need to do. We have hardly been able to start the work that one would need to do, and there's almost been an effort to hide one's head in the shale, one might say, about trying to look at the health aspects of this. So I'm going to take a look at, I'm going to show you some of these things. Well, there is a usual progression that we've seen through the years when we deal with environmental and occupational health issues. And I focus, let's not forget occupational health as well. It's very important. I probably won't say much more about it, but it is an issue. There's a potentially harmful societal industrial activity that occurs before all the health and safety information is available. There's reporting of adverse health outcomes, that people won't drink the water, won't, feel that they've been made sick. And there's a lot of people out there who are absolutely insistent they've been made sick by this drilling activity. It becomes major public concern, and you really can't get a cause and effect relationship developed, primarily because you don't have adequate exposure information. You don't really know whether someone was exposed or not. You also don't have the toxicological information. Now, I've been involved in this since serving in the Division of Air Pollution in the 1960s. That was before EPA was formed. And I had thought we'd gotten beyond this kind of sequence, that this was a historical picture. To be one of the most unhappy things about being in the middle of a Marcellus shale area in Pittsburgh is that this sort of says that we haven't gotten beyond that. We haven't really learned what we should have learned from our past experience. So, is health important? We just did a quick analysis of folks who appeared before the President Obama's advisory committee. It's the basically it's the Natural Gas Subcommittee of the Secretary of Energy Advisory Board as to the reasons of those who were opposed. And about 2/3 of them gave health concerns that they had or they had for their children, their families, as reasons for their opposition. So clearly health is of concern. And part of it comes because people really are confused and are sometimes angry over what seems to be competing information they're getting. I've set up two sets of basically 1 and 2 are opposed to each other, but they're all true on both of them. Now, how can you have contradictory information that's true? It's because of the way this message is being shaped in a way that really does confuse people and stresses people. It's true there is no proven incident in which hydrofracking has caused groundwater contamination. If you successfully release chemicals 5,000 foot underground, they probably will not get up to groundwater. Now, there's a whole thing about Pavilion, Wyoming. That's a distraction, that's not a 5,000 foot, and so I won't spend any time on it, given how late it is. But that's not what the public is concerned about. The public wants to know from the time that they start leveling the ground for that drilling rig till, 30 years from now, 20 years from now, when finally everybody leaves, is my groundwater going to get contaminated? And wow, there's been a number of examples, plenty of examples, you could say, of groundwater contamination with hydrofracking chemicals. Well, because the casing went, the drum got raw, some truck backed up into a drum that burst. There's all sorts of opportunities for this to occur. If you define hydrofracking very narrowly as saying, it's only the successful release 5,000 foot underground, of course you're going to be in a situation in which you can say, well, there's no proof of any problem. Well, the community is seeing the problems. I would argue that it seems to be that a lot of the research focus to date by the federal government has been to answer the question of whether the stuff from 5,000 foot underground gets to the surface. And that is sort of, one can be a little paranoid and say, well, that's because we already know probably what the answer is, and we don't want to ask these other questions, but maybe we'll get to them later. Is hydrofracking old or new? Well, again, we've heard this. Yeah, it's been around since the 80s, so why worry? Well, this picture is one you've seen before. Thank you, EIA, for providing it for us. Yeah, before it was done with perhaps 50,000 gallons of water. Now it's done with 5 million gallons of water. you've heard all about how the changes are in terms of all the different technology that's been added. The chemicals are different than they were before. They're much improved. They're much slicker. They're better biocides. To say that this is no different than to imply that we don't need to get anything more because we've already know that there's no problems, it's already been tested, is basically sort of, this is probably extreme, but saying that why worry about a hand grenade? It's no different than a firecracker. They're both explosives. Well, this is well beyond in terms of energy, in terms of risk, in terms of technology. We have to be careful. That doesn't mean it's necessarily going to cause harm, but there is no question that you cannot basically say not to worry because, after all, it has been around for decades. And we hear that over and over again, not only from industry, but from Congress. Don't worry, it's been around for decades, not a problem. So what are the issues that we are concerned with? Why is the public concerned? What can we say about these public issues? Well, stress is a large part of it, and I think the next slide in my thing, if it ever comes back in, will be on the issue. Is just an example of what happens when you have a secrecy about information. And we've gotten better on the secrecy issue here. But some of you, I'm sure, remember that there was a dispersant used in an unusual amount in the Gulf, close to 1 million gallons, with and this is the material safety data sheet, and it's got a proprietary organic sulfonic acid salt. If you go down to the Gulf, as I have frequently asked an audience, were you concerned about this? Are you concerned about the secrecy? Absolutely, yes. People talk about how they're stressed out about their secrecy there. If you ask them, did they find out what it was, the answer is no. I don't know, did any of you find out what it was? I usually say that I'm not going to ask for a show of hands, but how many of you take a laxative, a stool softener, occasionally? This turns out to be a common stool softener, probably sold in 1 million doses a day over the counter or prescribed by physicians. As a toxicologist, as a physician, I'm not worried about the effects on humans. I know what it's doing to the fish and the beasties in the Gulf. But it's not a human problem, but that they had to keep it secret. Why? They had to keep it secret, obviously not because the other companies couldn't figure out what it was. It's probably $1.25 worth of analytical thing to figure out what this is. EPA finally did release it on their website, but people don't know about that. And again, that secrecy contributes. What we have now is a situation in which we've come a long way from where we were before. The idea of 600 chemicals on a list is simply of no help to when somebody calls up and they say they've got symptoms. Could their symptoms be due to one of the chemicals? Well, of course. If you give me a list of 600 chemicals, I defy you to find a symptom or a disease that couldn't be due to one of those chemicals. So now, by narrowing it down to what the hydraulic, what's been added, we have a better chance of being able to find out something. There's still some confidential business information issues, but more importantly is that the law, for instance, in Pennsylvania that's just been passed that does a lot of increase in the amount of information about the fracking chemicals and the location, gives a complete buy to information about the chemicals that are coming up from below that are in the fracking flowback fluids, gives a complete buy to anything might be formed from terms of the chemical interactions of all these different chemicals. So you end up with a situation in which you still have lots of uncertainties. Part of the problem we have, though, is that we're simply not getting any health research moving forward. This is language from 3 executive orders, from the executive orders starting 3 different advisory commissions. One is President Obama's, another is from the governor of Maryland, a Democrat, another from the governor of Pennsylvania. All talk about the importance of health, unacceptable risks of adverse impacts to public health. We've published a paper, it just came out in Environmental Health Perspectives, analyzing the 52 members of these 3 organizations. Of these 3 advisory commissions. Good people, good hydrogeologists, I'm sure some members of AGU. The amount of people with any health background whatsoever is 0. Okay? Nobody with any health background is put on any of these advisory commissions having to do with health. In Pennsylvania, we ended up with this same bill that Rob talked about. It has 17 different organizations getting funds from the impact fee, state agencies, sub-agencies, commissions, the Boat and Fish Commission, all different organizations representing state agencies, local agencies that could reasonably be expected to deal with the impact. Not one penny went to the Department of Health. So the advisory kind of thing of saying, well, there ought to be some money to do some health studies, to develop a health registry even where people can call up and in a formal way get their complaints about their health registered, nothing. President Obama's commission, led by the Department of Energy, input from EPA and from Department of Interior, nothing from Health and Human Services. 8 state agencies involved between the 2 states, not the Department of Health in either case. Lots of very good environmental organizations, Trout Unlimited, Nature Conservancies, but not Children's Environmental Health Network or Group Against Smog and Pollution or, American Lung Association, any of the health-related ones. The issues are enormous. I think they're mainly the issues having to do with mixtures. It's really difficult to predict what's going to happen with a mixture. Rob mentioned coffee. That's a wonderful mixture. We've got lots of studies because humans have taken coffee. It's got over 1,000 chemicals in it. We can study gasoline, but we really need to study what these mixtures are going to do. It's not just the mixtures of the chemicals that are going down, because I think the industry does study that and study that well. I mean, if a chemical company comes in and said, I've got this new chemical which is going to be even slicker than the chemical you've got in there in terms of making slick water, they're going to test to see how it interacts with the existing chemicals that are going down there. But what about the chemicals that are being brought up? You heard about them. How do they interact with each of these? And again, we don't know. Here's the types of additives. You've been told about it. Finally, I want to talk about the accident issue versus the incident issue. This is really what we would call an accident. This is the Deepwater Horizon being hit by a comet. That's not an accident. That's an incident from a public health point of view. That's fully preventable. This is the kind of thing that you do if you work to prevent. This is Paul ONeill coming in as CEO of Alcoa and basically saying there shouldn't be any lost time, work time activities, days in a workforce. The only acceptable level is 0. And if, when I used to train occupational medicine residents, I'd say, well, look, when you go to look for a job at a corporation, you have to ask them whether or not an OSHA violation affects the bonus that a plant manager gets. And if it doesn't, you don't want to work in that company. Well, he fired the plant managers. Okay? That's the kind of culture of safety you need to protect the environment and to protect your workers. Here's what we have in Pennsylvania now. This is from our Frac Tracker group. This is violations per well for companies that have 10 or more wells, so they're not just the small mom and pop shops. And it's wells drilled during that period, and it's violations during another period. And basically, you've got 6 companies there which have never had a violation from the State Environmental Protection, and you've got another half dozen or so that have more than twice as many violations as they have wells. The reality is not these 6. The reality is this in terms of what the community is concerned about. And until we can get a handle on that, we cannot really protect public health in the way that needs to be protected. So I see 3 certainties that you can predict, and I've been saying this for a while. I was telling Chris Field how I recently have gotten credit for predicting the earthquakes because I had shown this slide. No, I didn't predict the earthquakes. What I predicted is surprises, because we always get surprises when these complex technical issues. We will continue to get surprises. There will be disease clusters, folks. That's going to happen. Now, whether or not they're causative or not, just think of this from a statistical point of view. Think of the number of communities that are involved. Think of the natural variation in disease occurrence. Inevitably, a community is going to notice that, gee, we got a couple of kids with autism. Or a couple of people with pancreatic cancer all died within a year. That didn't happen until they put up that drilling rig. It must be due to that. Well, what happens? Property values go down, newspaper reporters get involved, you have the inevitable lawsuits and the litigation secrecy and the difficulty to ever come to grips with this, statistically significant, but not necessarily causative. The decision can be made in terms of whether or not causation is going to occur with the kind of issues that we've been hearing about with health through science, or it could be made by the law in toxic tort cases. We're hoping it's done by science, but the longer we wait to get these kind of studies started that are needed to be able to answer the questions about health, the more likely this is going to be decided in court, and the more likely industry is going to lose out. Thank you.